the science behind retaining walls. Welcome to Blueprint to Reality. Today, we're exploring a fascinating aspect of civil engineering, retaining walls. These structures are far more than simple barriers. They are key elements in shaping landscapes, preventing disasters, and making construction on sloped or uneven ground possible. Whether it's holding back soil along highways or creating level terraces in residential areas, retaining walls are essential for safety and stability. Let's dive into the science and engineering behind them. What are retaining walls? Retaining walls are rigid structures used to hold back soil, rock, or other materials in a vertical or near-vertical position. They are commonly used when there's a need to contain different ground levels, such as in hilly or sloped terrain. Without these structures, soil could slide downhill due to gravity, causing erosion, landslides, or even damage to nearby buildings and infrastructure. Retaining walls help in maximizing usable land, creating flat surfaces for roads, buildings, and landscaping. Types of retaining walls. Civil engineers choose from several types of retaining walls, depending on soil conditions, load requirements, and space constraints. Gravity walls. These walls rely on their own mass to resist the pressure from behind. They are usually made of stone, concrete, or other heavy materials and are suitable for lower height walls. Cantilever walls. Built using reinforced concrete, these walls form an inverted T shape. They use a base slab and a vertical stem to leverage the soil's weight for stability. They are economical for medium-height walls. Sheet pile walls. Used in soft soil and tight spaces, these walls are made from steel, vinyl, or wood planks driven deep into the ground. They're ideal for temporary excavation or waterfronts. Anchored walls. These walls include cables or rods anchored deep into the soil or rock behind the wall. They're used when high retaining walls are required or when extra strength is needed in limited space. Each wall type has its own design logic and suitability, depending on environmental and engineering constraints. Forces acting on retaining walls. Retaining walls must resist various forces to remain stable and effective. Lateral earth pressure. This is the primary force pushing against the wall. It depends on the height of the wall, the type of soil, and the moisture content. Surcharge loads. These include additional pressures from vehicles, buildings, or storage loads behind the wall. Hydrostatic pressure. When water builds up behind a wall, it can significantly increase the load and cause failure if not properly drained. Seismic forces. In earthquake-prone areas, dynamic earth movements must be considered during design. Understanding and calculating these forces is crucial for ensuring that the wall does not slide, overturn, or collapse under pressure. Drainage and stability. One of the most critical aspects of retaining wall design is drainage. Water buildup behind the wall adds pressure and weakens the soil structure. To counter this, civil engineers incorporate weep holes, small openings at the bottom of the wall to allow water to escape. Drainage pipes, horizontal or sloped pipes behind the wall that redirect water away. Filter layers or geotextiles. These prevent soil from clogging drainage systems. Stability is ensured through careful analysis. Engineers calculate the factor of safety against sliding, overturning, and bearing capacity failure. Retaining walls must be carefully engineered to work with, not against, gravity and groundwater. Materials and construction. Retaining walls can be constructed from a wide range of materials, each chosen based on strength, aesthetics, and environmental conditions. Concrete. Common for cantilever and gravity walls due to its durability and strength. Stone or brick. Often used in landscaping for visual appeal and medium loads. Timber. A low-cost option for short-term or light-duty walls. Reinforced earth systems. These use soil reinforcement techniques like geogrids to create stable and flexible retaining structures. Construction involves several precise steps, including site preparation, excavation, foundation laying, wall assembly, backfilling, compaction, and installation of drainage. Civil engineers supervise every stage to ensure proper alignment, structural integrity, and safety compliance. Sustainability in retaining walls. Modern engineering encourages sustainable practices even in retaining wall design. Recycled materials, concrete with recycled aggregates, reused steel, or reclaimed bricks are increasingly common. Green retaining walls. Also known as living walls, these integrate vegetation, offering erosion control, stormwater absorption, and aesthetic beauty. Modular block systems. Precast blocks reduce waste and construction time while offering flexibility in design. Such innovations not only reduce the environmental footprint, but also enhance the lifespan and adaptability of retaining walls. Conclusion. Retaining walls are an impressive example of how civil engineering combines science, structure, and sustainability to solve real-world problems. From resisting earth pressures to managing water flow, these walls require thoughtful design and expert execution. Whether it's for a highway embankment or a garden terrace, the principles remain the same: safety, durability, and smart engineering. Thank you for watching Blueprint to Reality. If you found this video informative, don't forget to like, share, and subscribe for more deep dives into the world of civil and structural engineering. Stay curious, and see you in the next episode.